So, now we're ready to move on to sort of a more theoretical approach that chemists use when we're faced with a reaction whose energy change we'd like to know, but we can't study it directly in the lab. That could be for a variety of reasons. Can't get our hands on the chemicals that we need. Safety, might not be safe chemicals to work with. The amount of energy released might be too great or too small for us to work with safely on the too great side, or too small might mean we can't measure it actually. So there are a number of reasons that we are confronted with this situation where we can't directly measure our energy change. Thankfully, we have a law that's been developed and proven, not just made up, that helps us in these situations. And it's known as Hess's law of heat summation. It's a little wordy, but I think a picture will help us out. So in terms of definition, Hess's law says that the energy change of any reaction, if it can be expressed as the combination of a series of other reactions, the energy change equals the sum, the numerical sum, of the energy changes of the reactions in the series. So like I said, it's a little bit wordy, but I think a quick picture will clear up exactly what I mean. Let's say we had a reaction that was going to be something, pretty straightforward. A turning into Z. This is the reaction A to Z. And here's what the energy change is. We start here with A, we end here with Z. If we can't measure that reaction directly, we can find what delta H is if we can figure out some other combination of reactions that produces that same result. Maybe A turns into B in this first reaction, and then B turns into Z in the second reaction. And so the sum of these two reactions is A turning into Z. Or maybe in a different situation, if we have A turning into X, and then X plus B turns into Z plus A, this would give us the same total energy. The two A's would cancel out, the X's would cancel out, and we get, so I guess that should just be X producing Z plus A, so that it cancels out. A turning into Z that way as well. All right? Or maybe it was two A's. That's what I needed there. Okay? So if we can express any reaction as the combination of other reactions, the total energy change of that combination is equal to the energy change that we're interested in. So before we use this in some examples, I want to remind you of a few things about the enthalpies of reactions. Again, just generically speaking, if X turns into Y, has an energy change, an enthalpy change of negative 40 kilojoules per mole. We want to think about how this scales and changes with a few different scenarios in the lab, right? This is on a per mole basis. So if we use 2 moles of X and produced 2 moles of Y, the enthalpy would be double, right? The energy change would be negative 80 kilojoules. I'm not going to put the per mole part now because I'm now talking about the total energy. But this negative 80 is really 2 times the original negative 40 kilojoules per mole. It's the coefficient times the original enthalpy change. Or if we reverse this reaction somehow, if Y turned backwards into X, because of the first law of thermodynamics and that the energy change of the universe has to be constant, this reaction's energy change is just the opposite of the original X to Y. So this is 40 kilojoules per mole, or you could think of that as negative of the negative 40. Because what we did here is flipped the direction, and in chemistry that's equivalent to saying the negative of something, to take its opposite, all right, energetically speaking. Right. So let's see an example of how we use Hess's law to figure out the energy change of an overall reaction. It's a little bit like a puzzle. In using Hess's law, you're going to be presented with some small reactions typically that you have to figure out how to combine to produce your overall goal, your target reaction. So for example, let's say I knew that A plus B produces C, has an enthalpy of reaction of negative 60 kilojoules. And that a different reaction, D plus E, would produce B and 2 C's. The enthalpy change of this reaction is negative 25 kilojoules. Can we use this information to find delta H reaction of 2A plus 3B to produce D and E? So this is our target reaction. And so if you look at it, you can see that there's a lot of pieces or a lot of things down here that seem to be part of these reactions up here. But it's not going to be just as simple as, adding these two together. Just like when you get a puzzle, maybe, if you've ever worked on a puzzle, you open up the box and pour the pieces of the puzzle out. They don't just magically fall into place, right? Some of them are upside down, so you have to flip them over and they need rotated around. These reactions are really the same way. But this is going to guide what we do. All right. So one thing that I'm looking at here is I see that in my overall reaction I want 2 A's. I've got a reaction up here that involves a single A, so I'm going to just double that in its scale, just like I did a second ago. And I'm going to write 2 times the A plus B to produce C. When I do that, the energy is going to be 2 times the original negative 60 kilojoules. Just like it was with our X to Y a second ago. And now a couple of reactions have B in them, which might make B a little bit tricky. But this bottom reaction is the only place where I have D and E. So I'm going to use it to guide me for getting my D and E. Unfortunately, it's on the wrong side. But all reactions are reversible. So I can just change the direction of this reaction and write B plus 2C will give me D and E. And as I just saw with my X reaction a minute ago, what that means I do is take negative 1 times the negative 25 kilojoules. So let's see if this works. When you distribute your 2 to your A, B, and C, the arrows are like an equal sign in algebra. Anything that's present equally on both sides can be canceled out. So this gave me 2 C's, which would now reduce, and the C's drop out. I have 2 A's, I have 2 B's plus a third B, so I have 3 B's, and then on the right side I'm left with D and E, which lo and behold is my target reaction. So I showed that this reaction is the sum of some combination of other reactions. So the energy change in my target reaction then is just the sum taking into account what I did to the reactions. So it would be the 2 times the negative 60 plus the negative 1 times the negative 25, or negative 95 kilojoules. So that is the delta H of this reaction. So we can use Hess's law to find the enthalpy changes of a number of reactions when we have related information to them. The trick is finding this related information. And what we're going to do in the next segment is be able to, rather than have to be given these reactions, we're going to, quote, make them up on our own. But we're going to use real reactions. But I'll show you how we can make any set of reactions for ourselves. So that'll be the next segment. I'll see you in a minute.